Hey folks, Professor Gray here, ready to talk to you about more of the binomial distribution. Now, earlier we left off talking about the binomial distribution, and a binomial distribution has four characteristics. One, the procedure has a fixed number of trials. Each trial is independent, and each trial must have all outcomes classified into two categories, usually success or failure. And the probability of success remains the same for all trials. Here are some additional problems based upon the binomial distribution. Based on a poll, there's a 0.85 probability that a randomly selected adult knows what Twitter is. 8 adults are selected. Let's find the following probabilities. First off, is this a binomial distribution? Well, we can verify that it is because there are a fixed number of trials. That would be 8 adults. The outcomes are either going to be success or failure. Either the adult knows what Twitter is or they do not. We can assume that those trials are independent because just because I know what Twitter is does not necessarily mean that another randomly selected adult would know what Twitter is. And the probability of success is the same throughout all the trials. That would be the 0.85 probability that's going to stay constant. So for number 22, let's find the probability that half of these 8 adults know what Twitter is. Well, what is half of 8? That would be 4. So for number 22, first, the probability statement. We're looking for the probability that x is equal to half of 8, which is 4. And since we're looking for exactly 4 successes, we can use the calculator command binom PDF. PDF is used for one number of successes. CDF is used for a cumulative total of the probabilities of more than one success. So on my calculator, I go to second bars, that leads to the distribution menu, and scroll down to binom PDF. Once I reach that, my syntax is the number of trials first. Well, in this scenario, I have 8 adults selected, that's 8 trials. Comma, probability of success is 0.85, that's the probability that one of these adults know what Twitter is. Comma, and the last number is my number of successes, that would be 4 per the problem. I find my answer, and there it is. Now, in a previous video, we made an entire table of binomial distribution probabilities, and then we answered questions about them. Using the calculator and getting the hang of what the calculator does, we don't have to make that table every single time. The table is a teaching tool. The idea is to get to where you can look at the problem and decide what calculator command to use and be able to solve the problem using the calculator and fewer steps. All right, so 0.0185 is my answer, rounded to 4 places. Let's take a look at number 23. Find the probability that 7 or 8 of the selected adults know what Twitter is. Okay, so this would be the probability that x is 7 or 8. Well, to find that out, I can use binom PDF and find the probability that out of 8 adults with a 0.85 success rate, exactly 7 will know what Twitter is. Or, in probability, tells me to add. So I can add that to binom PDF, this time with 8 trials, 0.85, and 8 successes. So the first part gives me 7 successes. I add that to 8 successes and I get my total probability. So I'm going to do just that. All right, I type in Binomial PDF for the first part, then add, so plus, and then second bars again, and I can put in the other probability. The calculator does not mind having that all on one line, as long as you be sure to close your parentheses after the binom command. And I get my answer. .6572 is my answer. Let's take a look at some more examples. Number 24, same scenario. The probability that fewer than 4 of the selected adults know what Twitter is. All right, for number 24, I'd find the probability that x is less than, that'd be fewer than 4. Now I'm going to round, so I put my approximately equals in. Fewer than 4. Well, let's think about the different numbers of successes I could have. I could have 0, 1, 2, 3, 4, 5, 6, 7, or 8. And fewer than 4 would be anything from 3 down. So there are two different ways to approach this problem. I could do binomial PDF of 0 successes, then 1 success, 2 success, and 3 success. And I would add all those together and I would get the right answer. That is completely correct. It would result in a correct response. There's a faster way, however. If you recall the table we made in previous video, we can use binomial CDF, and the calculator will find the cumulative probability for us. It will count the probabilities right on up. So 8 trials, 0.85 success rate. And the last number is where I want the calculator to stop. So the calculator will start at 0 successes and keep counting up. We want it to stop at 3. Now I'll find that using technology. And I get my answer. That's my probability. All right, let's try number 25. Probability that 6 or more. So 25. Looking for the probability that x is 6 or more, so greater than or equal to 6. Well, let's think about the numbers of successes I'm interested in. And there is no shame in listing out your numbers of successes to get a good idea visually what you're interested in. Well, I need everything bigger than or equal to 6, so that would be all of these. Well, I can do binomial PDF of 6 successes, 7, and 8, and add them all together, and I would get the correct answer. You think of a faster way, or maybe a way with fewer steps? There is another way to do that. If I take a look at the stuff less than 6, those are the things I don't want. So if I get rid of what I don't want, I'll be left with what I do want. Oh, well, this is a probability distribution so the sum of all of these probabilities would be 1. If I take the whole thing, that'd be 1 or 100%. I'll subtract off binomial CDF, 8 trials, 0.85 success rate, and everything from 0 up to 5. So if I take 100% or 1 and subtract off the probabilities from 0 up to 5, I'll be left with the probabilities of 6, 7, and 8 combined. So I'm getting rid of what I don't want, that's 5 and down. I'm left with what I do want, that's 6 and up. When I put that in a calculator, I can put it in just as it's written, 1 minus first, then second bars, second bars, binomial CDF, trials, probability of success, biggest number that I don't want, and I get my answer. So there's a 0.8948 chance or probability that 6, 7, or 8 out of these 8 people will know what Twitter is. I can use the binomial CDF and subtracting from 1 as the complement rule to get the probabilities in less steps. Let's do another one. Number 26. Find the probability that less than 5 or more than 5 of these adults know what Twitter is. Probability X is less than 5 or X is more than 5. Let's think about how many successes I'm really interested in. If I list out my different possibilities for success, I want everything less than 5, that's 4 and down. I want everything bigger than 5, that's 6 and up. So I could find the probability of 0, 1, 2, 3, 4, 6, 7, 8 successes and add those all together. Is there a faster way? Why, yes, there is. Use the complement. 1 minus binomial PDF, 8 successes, 0.85 success rate, and 5 successes that I do not want. By using the complement, I'm finding the probability of exactly 5 successes. That's this one in the middle. That's the one I don't want. So if I subtract it from 1, I get rid of it. And what I'm left with is everything I originally wanted. This cuts out quite a few steps. And I get my answer. 0.9161. Let's talk about the descriptive statistics for the binomial distribution. The mean is found in a way that is significantly shorter than other ways that we've found the mean. You multiply n, that's the number of trials, by p, that's the probability of success. For standard deviation, multiply n times p times q and take the square root. For the variance, square the standard deviation or multiply n times p times q and do not take the square root. What was q again? I'm so glad you asked. Remember that q is 1 minus p. It's the complement of p, or the probability of failure. Let's do a few of these problems. Number 27. Let's find the descriptive statistics for this scenario. Based on a poll, 30% of U.S. adults agree with a new bill to raise taxes. Assume that 4 adults are randomly selected. Oh, well, that's the scenario from the previous video. Well, to find the mean, that'd be mu, we multiply n times p. And the number of trials was 4. 4 adults were selected. Probability of success is 30% or 0.30. Be sure to turn that, convert that over to a decimal. And at that point, if I use the calculator, I can confirm that 4 times 0.30 is 1.2. That's my answer for the mean. All right, now standard deviation. Standard deviation, that's the square root of n times p times q. As stated before, n is the number of trials, that's 4. P is the probability of success, 0.30. Q is the probability of failure. Well, if there's a 30% chance that you'll succeed, probability you'll fail is 0.70. And of course, we take the square root at the very end. We'll round that to 1 decimal place since the mean is in 1 decimal place. Stay consistent, 0.9 approximately. 2 out of 3, that's mean and standard deviation. Now the variance. For the variance, that's sigma squared. Formula is n times p times q. This time I don't take the square root. I'll multiply 4 times 0.3 times 0.7. I get 0.84, again rounded to 1 decimal place. That's 0.8. Now for another example. Number 28. Based on a poll, there's a 0.85% chance, or excuse me, not a percent chance, there's a 0.85 probability that a randomly selected adult knows what Twitter is. This is the second scenario that we talked about. 8 adults are randomly selected. Let's find the descriptive statistics. First, the mean. That's no problem. N times P, no problem. N is the trials. That's 8. P is the probability of success, 0.85. I can use my calculator. And I get exactly 6.8. That's the mean. Standard deviation, square root of N times P times Q, where Q is the complement of P. So that'd be the square root of 8 times 0.85 times, well, Q is 1 minus P, so 1 minus P, 1 minus 0.85 is 0.15. Then I find the square root of that product. And we'll round that to 1 decimal place as well. Once it's rounded, you get 1.0. I leave the 0.0 because it is rounded. One last thing, let's do the variance. That's N times P times Q. So 8 times 0.85 times 0.15. And I get approximately 1.0 for that as well, which makes sense. Those are the descriptive statistics for binomial scenarios. Well, let's talk about expected value. Number 29, how many answers should you expect to get correct on a multiple choice pop quiz that has 5 questions with 4 choices for each question? Expected value is calculated the same way as the mean. So all this problem is really asking for is the mean. And because this is binomial, I know that because it has the 4 characteristics. Fixed number of trials, that's the number of questions. Trials are independent? Sure. Each trial results in one of 2 outcomes. Well, you either get it correct or you don't. And the probability of success, getting something correct, is the same for all trials. Sure, there is a 1 out of 4 chance that you will get the correct multiple choice option. So to find the mean of this scenario, I'm going to take my number of trials, it's 5 questions, times my probability of success, 0.25 or 1/4. Multiply those out, and hey, if you've got 5 quarters, you've got $1.25. So on average, if you're taking a 5-question multiple choice pop quiz and there's 4 choices for each question, you would expect to get 1.25 of them correct if you are guessing. If you are answering randomly, you're much better off to actually know the answers. But if you are randomly picking, you would expect to get 1.25 of them correct. Number 30, would a score of 4 correct be considered unusual? For unusual values, those are 2 standard deviations above or below the mean. So, my mean, I just found that in number 29, was 1.25. I'll go 2 standard deviations above the mean. That's a 2 sigma. 2 standard deviations below the mean, and I'll make boundaries. Anything outside those boundaries will be unusual. Anything that's not will be not unusual. To do that, I got to know what sigma is. So sigma is the square root of n times p times q, which would be the square root of 5 times 0.25 times, well, probability of getting one right is 0.25. Probability of getting one wrong would be 0.75. And we'll round that to 2 places. I get about 0.97. That's for the standard deviation. So 2 times 0.97 is 1.94. 1.25 plus 1.94 will give me my upper bound. All right, so my upper bound is at 3.19. My upper bound, I take 1.25 and subtract 1.94. And I get a negative 0.69. So negative 0.69. All right, now I've got those boundaries set up. Here's the part where I have to make a decision. Is 4 inside the boundaries or outside of them? And as you can see, 4 would be greater than 3.19, so a score of 4 correct would be unusual. That's a yes. Well, as the number of trials increase in a binomial distribution, or as n, that's the number of trials, gets bigger, the binomial distribution becomes a normal distribution eventually. Unimodal, symmetric, bell-shaped, the normal distribution. So in videos to come, we'll talk more about the normal distribution.